going to assume a curved mirror. Now, when you look at this right here, you might not look at that and go, huh, yeah, that's definitely a curved mirror. So let me state that it's a curved mirror. So if light's coming in from an infinite distance away, because it's curved, and let's make it concave. I'm going to make this concave. Light's going to bounce off of it. Now, if light's coming in straight in from some far distance away, it's going to hit this, and then it's going to bounce and go through some point here. This is known as the focal point. If you've seen the big satellite dishes, I'm thinking of the one in, I think, Central America, for picking up light coming in from.
One of those collapsed recently.
Yeah, that's one of those. Do you remember where that was?
I know it begins with an A, I can't pronounce it. I know it's the one that broke. Well, it collapsed.
I think we're in the same boat there. I remember the A, but that was about it.
Isn't this how glasses work as well?
Yeah.
Glasses?
Yes.
That would be a lens. There's something very similar. There's a focal point for.
Or a mirror and a lens, yeah.
Yeah. We'll get into the contrast at some point.
Yeah, I think these are I think they're convex glasses, lenses.
Convex concave depends on how it's bent. If you are nearsighted, it is a diverging lens. If you're farsighted, it's a converging lens.
Yeah, I think I'm nearsighted.
This question, is that clear and that's less clear?
Or I think it's more because of what you see with my eye.
Oh, okay. Anyway,
I don't remember.
we're all mirrors right now except lenses. Now, so I'm going to label this distance here, from here to here, as F. I also know that light that comes in, that hits the central point of the mirror, is just going to bounce straight back out. So even if I drew it curved, light that comes in is going to go through the focal point. Light that goes through the center is going to, there's my angle of incident, my angle of reflection. Well, the same thing's happening here. If I draw a line that's tangent to my curve, then that angle of incidence, called theta I2, is going to be equal to that angle of reflection, 2. Nice tiny print. And what I want to do, I need to draw that better. So what I'm going to do is I'm going to start that further back. It doesn't necessarily affect your nose, but it depends on how much I want to warp this. So I'm going to start it here. Wow, that is still not what I want to draw. There's my central axis right there. I had light coming in, going through. Let's make that focal point closer, and then there we go. That's closer to where I want, although apparently I can't draw straight lines. So if I have an object here, so light that is going by the top here, that hits the top, that light is going to meet again here. This would be my image. This point right here is my focal point. So let's define some distances. So from the mirror to the focal point, labeling as F. From the mirror to where the object is, I'm going to label it as P. And from the image to the mirror, I'm going to label it as Q. So I have three primary objects, or three primary distances. I have object distance, image distance, and focal distance. And surely there's a relationship between those three things. Yes, there is. So let's do it. Hopefully find a marker that's dark enough. So given my three lines here, this point right here, so if my object, we're going to say is height h sub 0, and my image is height h sub I. I want to see where this line right here and this line right here meet. So the upper purple line I'm going to label as A, and the bottom purple line I'm going to label as B. Well, this point, then, if this is my origin right here, if this is 0, 0, then, actually, you know, ultimately, yeah, I do want that 0, 0. So this is the point right here, negative P, comma, H sub 0. That's that data point right there. Basically, think of it, we're dealing with a graph here. This right here would be the position negative Q, comma, H sub I. Notice at this point right here, I've now established that for this situation here, H of I is a negative number. That's going to come into play later on. This point right here is the point 0, H sub 0. And this point right here is the point negative F 0. All right, so let's come up with our equations of our lines. I'm going to basically put these lines in the y is equal to slope x plus b form. So, the slope for line A. Yes?
Where are you in the book?
Chapter 34.
I meant the page number, sorry.
34.5.
Okay, the mirror equation, right? I just wanted to ask, because I feel like I'm starting to run out of paper around my legal pad.
All right, so equation A right here. Well, how do you find the slope of a line?
Y2 minus y1 over x2 minus x1.
All right. So my slope for line A, I'm going to take I got 2 points right here, so I'm going to take those. And so I've got y2 minus y1 over x2 minus x1. So h naught over f. It's a positive fraction because focal length is a positive number here, and h0 is positive, and so, it's a positive slope going that way. My intercept, where does this line reach my y-axis here? Again, if we treat this as y and this is x. What's my y-intercept?
0. Why not? Right? 0.
Not 0. Line A. Line B is 0, but line A.
Yeah, H naught.
Yep, h naught. And so my formula for equation A is y is equal to h sub 0, height of the object divided by the focal length, times x plus h sub 0.
Oh.
Now, line B. What's the slope of line B?
Isn't it HI over?
What?
HI over F? Or line?
No, line B doesn't go through the focal point. This is line B down here.
Yeah.
Is 0 minus HI over 0 minus negative Q.
Which is negative hi over q. Remember earlier that hi is a negative number here, and so the slope is positive overall if you actually plugged in a value for hi and for q. So the slope of this line is y equals negative hi over q. Times x plus 0. Don't have to write the plus 0, but the intercept is right there at the origin.
Minus x?
Minus, no, that's x.
Oh, okay.
Why are you keeping the slope as negative if it's a negative number?
Hi is a negative number.
Right,
So negative of that negative number becomes positive.
so why do you leave the negative sign there?
Because of the convention that we'll eventually hit that.
Okay.
I think it's the numerator as well being negative.
The numerator as,
Negative HI.
negative hi is a positive number.
Oh.
Hi is a negative number.
Oh.
Basically, the convention is that whatever side the object's on in terms of above or below, that's considered the positive side. So if my image is below that, that will end up being a negative number.
Okay.
So if you actually solve for hi and it ends up being a negative number, you go, oh, it's inverted. That's the convention
Okay.
we're working with here. We'll eventually plug numbers in. All right, so now, I know that the angle of incidence here, this theta sub I and theta sub R, are equal to each other. Because we have a nice perfect mirror. And I also have two right triangles. I've got this triangle up on top, where this distance here is h sub 0, and this distance here is p. And I have this angle here. So I know the tangent of theta is equal to the opposite over the opposite over the adjacent. If I look at the bottom triangle, since I'm dealing with actual distances here, this is negative h sub I, and this here is q. When I'm doing the trig, I need an actual length here. I don't need a, I'm not looking at a coordinate. So tangent of theta from the bottom triangle is negative hi over q. So my equation over here, therefore, can be written as h0 over p times x. Just taking my slope. That's just my slope of line B. And now, let's figure out where x is. In other words, let's make these two equations, figure out where they meet. That's what I'm going for. So I have HO over F, x plus HO is equal to HO over P times x. I know that they're going to meet at wherever the image is. That's what defines where the image is. In other words, x here is the letter q, so this is h naught over f times q plus h naught is equal to h naught over p times q. That's where the two lines meet. Lines meet at image. Please. Oh. That should be negative q. At x equals negative q. And so now we should be able to come up with a relationship here, assuming I haven't screwed up a negative sign somewhere. So negative q h over f plus h0 is equal to negative h naught q over p. Let's get a common denominator, or let's get rid of the fraction, so let's multiply everything by fp. And over h sub naught. I have h sub 0 in every term, so I can get rid of that. Cancel out that one, and that one. Don't forget there's a 1 left over there. So I get negative, sorry, I'm taking an extra step here, but negative PQ plus FP equals negative FQ. I'm going to subtract FP from both sides, bring this over to here. So I have negative PQ is equal to negative FQ minus FP. Let's go ahead and simplify, multiply by negative 1, so we get rid of our negatives. And now I'm going to divide both sides by FPQ. And so I have 1 over F equals 1 over P plus 1 over Q. That is the relationship. And that relationship works for lenses as well. So the same relationship works for concave mirrors, convex mirrors, concave lenses, convex lenses, or diverging lenses and converging lenses. The trick is knowing the convention about when are things positive, when are things negative. All right, questions to there before I talk about magnification? Alright, magnification deals with what is the height of the image versus the height of the object. So if the image is bigger than the object, magnification is bigger than 1. If the image is less than the object, magnification is less than 1. And then so from this relationship here, we get negative Q over P. So if I have a concave mirror, focal length equal to 10 centimeters, and I have a 3 centimeter tall object, 15 centimeters from the mirror. Nature and facts about, do it this way. Image is, do it that way, question mark. We should be able to know what the final height is of the image. We should be able to, so we should know where the image is, whether it's inverted or upright, and the size of the image. So let's give ourselves some space using this. So 1 over the focal length, which is 15, nope, which is 10, equals 1 over the distance from the object to the mirror. So that's 15 plus 1 over Q. So I have 1/10 minus 1/15 equals 1 over Q. This is 1/30 equals 1 over Q. That's 2/30, 3/30, 1/30, okay. And so Q is equal to 30 centimeters. My magnification, which is H image over H object, the height of the image over the height of the object, is H image over 3 centimeters. And that's equal to negative Q over P. So negative Q over P, which is negative 30 over 15, which is negative 2. So my magnification is negative 2. The negative means that it's inverted, facing, so it's the opposite, pointing down if the object's up, and it's twice as big. So the image is 30 centimeters in front of mirror. It is inverted, and it is 6 centimeters tall. Now let's see if we can actually find that geometrically. This next bit I've done many times over the years, and I will say that sometimes it works out well, sometimes it doesn't. Depends on my skill in drawing. So I'm gonna put my mirror there. So the object is 15 centimeters from it. So that's where the object is, and that's where the focal length is. So there's my focal point. That's my mirror. My object is 3 centimeters tall. So there's my object, 3 centimeters tall, 15 centimeters in front of the mirror, and my focal point is 10 centimeters away. I know light that's coming from an infinite distance away will pass through the top, hit that, and then go through the focal point. So let's draw that. That look parallel to the brown line?
Yes.
It's gonna hit the mirror and then bounce through here. I know light that passes across the tip here and hits the very center of the mirror is gonna bounce back at the same angle. So this is light coming in this way. It's gonna bounce back the same, so let's put a little 3 centimeter mark here, so 1, 2, 3. It intersects here. And it's not coming out particularly well. So just doing the line drawings here, it is 4 centimeters tall and 21.5 centimeters away. Yeah. I should have doubled the numbers. Doubled my scale. Anyway, I believe that part true. It's inverted, that match. Two more things before I let you go. I know the excitement's building up really high right now. Let's do it. If I have a curved mirror here, if I have a light that shines and hits the mirror and then bounces right back to where it came from, that means that I must be going through basically the center of the curve. This is part of a giant circle here, and this is basically the radius of the mirror. Radius of curvature, better wording. So light that goes through there and bounces back through the exact same spot, my image and object are basically the same because the light's just passing right through it. So 1 over f in this particular case would be 1 over r plus 1 over r, which is 2 over r. And so my focal length is r over 2. In other words, for a mirror, the radius of curvature is twice the focal length. So I didn't have to give you the focal length, I could have just given you the radius of curvature, but from this, I know the radius of curvature is equal to 20 centimeters. And the other thing I want to deal with is similar to that, except now I want to make P, so the focal length, 10 centimeters. Let's make P 5 centimeters. What is Q? So 1 over 5 plus 1 over Q is equal to 1 over 10. 1 over Q is equal to 1 over 10 minus 1/5, which is you seem not to agree with what you saw.
Yeah, 1/10 minus 1/5, I got negative 1/10.
So Q is negative 10 centimeters. Which means my magnification,
Well, that makes sense.
it would be negative of negative 10 over the object was 15 centimeters away. Oops. I meant to make this. No. 5 is right. That's right. Over 5 or 2. My magnification is positive. What does that tell you about the image?
You got 100.
Sorry?
It's up right.
All right. I think that's what you were gesturing.
Yeah.
What does a Q of negative 10 mean? Negative 10 centimeters.
It's the other side of the mirror.
Yes, absolutely. The image is going to be over here. And that, we'll wait till, I guess, next Wednesday.
That shouldn't happen. Or it doesn't look like it should happen.
But it does.
So.
I mean, you have dealt with images being on the other side of the mirror before. Every time you have looked into a mirror, you see an image that is behind the mirror.
Oh, an absolute reflection. Well, that's what it is, absolute reflection.
If you think about a regular flat mirror, the focal length of a flat mirror is an infinite distance away. So this would be infinity for a flat mirror. In essence, this fraction here is close enough to 0. So 0 is equal to 1 over P plus 1 over Q, which only works if P is equal to negative Q. So if you're 10 centimeters